Reading Barbary, and this is my Physics 2212, Lab 4 on bar magnets. For an introduction, the point of this lab was to examine how the Biot-Savart law works with a bar magnet. The law and bar magnet were tested by measuring the magnetic force from multiple different locations with an app on a phone. In the end, the magnetic field parallel to the bar magnet was found to go from the South Pole to the North Pole. The field perpendicular went from the North Pole to the South. In the lab, the bar magnet was the system and everything else was the surroundings. The lab, the Biot-Savart law. The law gives the magnetic field a point due to a current, and the law is seen here. And then the magnetic field due to a dipole is shown by this long equation. Here in the lab, first, the magnometer inside the phone has to be found. To do this, the ruler is placed on the north to south line, then the phone is slid up and down until the x component is at a maximum and the y component is at a minimum. A piece of tape is put across this line, as you can see here. And then a second piece of tape is placed in a similar way, and the magnometer is at the upper edge of both pieces of tape, and we marked it with an X. For the on-axis procedure, the phone is kept on the meter stick and moved away from the bar magnet. The distance from the bar magnet is recorded when the magnetic field in the x direction is 20 microteslas. And the distances are recorded at 70, 120, 170, and 220 microteslas also. For the off-axis procedure, by using two rulers, a total distance is able to be found with the Pythagorean theorem. The magnetic field in the x, y, and z components are measured at different distances. And here in this model, you can see that this is the total distance and this is the y component and x component of that distance. For the on-axis data, it's found here with all the distances, and this is from the 20, 70, 120, 170, and 220 microteslas. And this data can be plotted here, and then the line of best fit can be made from that plot. And in this line of best fit, n equals negative 2.9304, and the natural log of k equals negative 14.783, and you'll see why these numbers are important later. For the off-axis data, it was plugged into this table, and there's the distances and then the Earth's magnetic field, which is subtracted from the total to get the magnetic field just from the bar magnet, and some other data. For the coding in this lab, the magnitude of magnetic force was put in, and then these were the observation locations created, and those observation locations were used for these arrows, and this is an arrow for the on-axis, the perpendicular, and the diagonal fields. And that code outputs this model, which shows the bar magnet in the middle, and then some of the different fields around and their magnitudes. And that is the same as these vectors here. For the calculations, the magnetic field of the bar is given by this formula here, and the magnetic field of a dipole is given by this here. And these equations can be set equal to each other, and by using n as roughly -3 and the natural log of k, which we found earlier, we can find that mu is 1.9 amps per meter squared. What if number 1? What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? The Earth's magnetic field would superpose with the bar magnet's magnetic field, which would ruin the data for the bar. What if number 2? What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? The magnitude of the measurements would double, but the directions would stay the same. Assumptions and possible errors. Assumptions. The bar magnet was assumed to act as a perfect magnetic dipole, and a possible error was the distances could be slightly off due to human error. In conclusion, the physics principles were able to work nicely with our experiment due to only a small assumption, which was the bar magnet being the same as a dipole.